Hi, and welcome to Reliability at Scale. If you are attending this conference, you likely care about building resilient systems, and so do I. Yet, in this talk, I actually want to I want to advocate that it's not enough to just build resilient systems, and that we want our systems to be recoverable as well. But first, a couple of words about me. My name is Joe McGaramoff, and I am an engineer at Amazon. I've been with Amazon for almost 20 years. And now Amazon has a very peculiar culture. If you have a long tenure with the company, one of the subtle perks you get is that the color of your badge changes. In my case, I have a purple badge. But an even bigger upside is that you get a chance to work on a very diverse set of services and businesses. In my case, I've worked on systems ranging from payment processors to public APIs, and for the last 10 years, I've been with Amazon Web Services, where I work on our computer networking services. And I think you can imagine this is a very different domains. Yet, despite their differences, they all had one thing in common. Building resilient systems mattered in every single one of them. And it mattered because that's what our customers expected from us. Now, if we look at the history of engineering, one of the best ways humans learn to build reliable systems is through redundancy. With redundancy, small increases in cost can provide large increases in reliability. And that is a very powerful, very desirable property for real world systems. Perhaps most familiar examples of that are modern airplanes, where virtually every critical system has built-in redundancy. 20 years ago, on my very first Amazon team, we were already building distributed systems that use commodity servers and that use many commodity servers. And in such systems, the reliability of the whole system was higher than reliability of the individual servers. Over the years, we've also learned that redundancy alone is not enough, and that we needed to change our engineering practices as well. For example, human intuitions about behaviors of complex systems tend to be wrong. And so our teams use techniques and tools like fault injection simulator or game day testing to inject failures into our systems and verify that these systems behave the way we expect them to, the way we want them to. We also believe that you need a culture that continuously focuses on reliability. At AWS, an important part of our culture is a process we call correction of errors. In this process, after every unexpected failure, our teams write up a detailed analysis of why the failure occurred, and then they list a list of time-bound action items that they commit to deliver, action items that would prevent similar failures from happening again in the future. Over the last few years, we've also been investing in techniques like formal methods that help us rigorously verify critical algorithms and protocols within our systems, or approaches like cellular architectures that help us reduce the risk of scale-related failures. But one thing that anybody who works on resilient systems for a long time learns is that it's also important to have humility. And precisely because the universe is really creative at making things fail. A story I want to tell today is that of Qantas Flight 32. Qantas 32 was an Airbus 380 flight from Singapore to Sydney. Shortly after takeoff, the airplane suffered a failure in one of its engines. Now, Airbus 380 is a modern plane, and like all modern planes, it has a lot of redundancy. It has four redundant engines, it has redundant hydraulic and electrical systems, and so on. And the airline industry also spends a lot of time. It has some of the most rigorous manufacturing and testing processes. And so an engine failure was certainly a situation this airplane and its crew should have been well equipped to handle. Unfortunately, this turned out to be a no ordinary type of engine failure. An oil pipe within the engine had a manufacturing defect, and that defect caused the oil to leak into the engine. That oil then proceeded to explode, and due to another design flaw, the engine housing did not contain that explosion. Now, modern jet engines have a lot of angular momentum. The rotors spin at hundreds of rotations per second. So, so when this oil exploded, little pieces of engine flew in different directions like shrapnels. And some of those pieces hit the airplane body. Thankfully, no passengers were hit, but the damage to the plane was extensive. As bad luck had it, these little pieces of shrapnel damaged a bunch of critical systems on the plane, including engine and flight controls. And so, to their surprise, the crew didn't just see engine failure light go on. They saw dozens of alarms telling them that various systems across the plane were experiencing a failure, including some systems that should have been redundant to begin with. And if you've ever been in the trenches when a complex system fails, then you know that alarm overload is a real problem. And often it can be hard to tell what is the cause and what is the effect, and where you actually need to spend your attention, where you need to focus your attention. Luckily, this story does have a happy ending. The commercial airline industry puts a lot of time and effort into training their crews to recover from a wide range of failures. And in turn, modern aircraft are really engineered to help that recovery, even when the plane is experiencing many different failures. In this case, after realizing that this wasn't a typical engine failure, one of the most important decisions the crew made was to focus on what still worked and focus on how to recover. The captain knew that in order to recover, they needed to land the plane. And in order to land the plane, they needed to get enough control of the airplane. And so, after spending some time and putting effort to recover just enough control of the airplane, they managed to safely land at a nearby airport. And, and that's an important lesson to take from the story. Finding the root cause can seem important for recovery, but failures in complex systems rarely have a single root cause, precisely because resilient systems tend to be hardened, they tend to be resilient to single failures. Instead, such failures often have a trigger that leads to a series of cascading failures. And what aviation industry teaches is that when failures occur, it's more important to focus on quick recovery. And you still need to understand the causes of failures because you want to harden the system against future failures. But that can happen at a later time. And so this is the mindset we want our teams to embrace. At Amazon, we put a lot of effort into building systems that are resilient, even when underlying components fail. But if there's ever an unexpected outage, we want our teams and our systems to be optimized for quick recovery. And there's a good reason for that. Longer outages have higher impact on the customers, and that relationship may actually be super linear. But how do we go about building systems that are easy to recover? To share one of the approaches, I want to draw a parallel to a job I had many years ago. When I was a teenager, I had a part-time job as an IT admin at a local college. And now, one of my many responsibilities was fixing computer problems that are reported by our users. Clearly, nobody enjoys computer problems, especially when you have an assignment due. So I was told to solve these problems as quickly as possible. I needed to solve these problems as quickly as possible. And to do that, when presented with the problems, oftentimes the very first step I would take is turn that computer off and on again. And in fact, if you deal with technical support for any consumer product, it's often the very first step that you will be asked to try. And it's easy to roll your eyes and smile at this approach. It just seems so lazy and unscientific. But there's actually good science behind why this works. Computers and most consumer devices tend to have a lot of internal state. And many failures happen because the application or the operating system got into a state that it just wasn't programmed to handle. And then it gets stuck in that state. If you ever played Tetris, you might be familiar with that feeling. Now, I'm not a great Tetris player, so I can easily get myself wedged in the jam. And it's certainly possible to work your way out of it by carefully placing the bricks just right and having good dexterity and being very strategic about how you place the bricks. And in some sense, it might even be very satisfying when you do. But it's just so much quicker to reset the level into a known clean state and start over again. And when you power your computer off and on again, you're effectively doing just that. And I think this is a principle we can apply to our at scale distributed systems too. Complex systems also have a lot of state. They tend to have caches and work queues and connection pools and thread pools and so on. And what's worse, that state tends to interact in non-trivial ways. And so there's a whole category of failures that happen because the system gets into an unexpected state that it just wasn't prepared to handle. And just like a computer, the fastest way to recover might be to turn the system off and on again. Unfortunately, resilient systems tend to resist that. Just for no other reason that a lot of engineering effort goes into making sure that the system stays up no matter what. A large scale system might be in constant state of partial restart due to deployments or host failures, but a total clean shutdown may be something that such a system has never experienced. And in fact, many resilient systems might be running continuously since the very first day they launched. Because of that, it can take intentional engineering choices to build a system that is capable of starting quickly and safely. You might be thinking, I restart my system all the time when I deploy, or that I use containers and restarting my system is really easy for me. But ask yourself, when was the last time you really cleared all ephemeral state from your system? And how long did it take? And if you set out to build something like that, there's lots of ways to go about it. You could build a big red button that powers off your infrastructure and restarts all your hosts, or you can implement a control plane API that resets the entire fleet in a controlled fashion. At Amazon, we tend to worry a lot about relying on tools that are only used infrequently because we found out that such tools tend to let us down during emergencies. So for us, the most common approach is to use the same system we use for deployments, just adjusting velocity control to perform a really rapid zero change deployment and have that go through the system. But of course, turning off is only half of the story. We really want the system to turn back again. And that's not always easy for complex systems. One of the most memorable failures I've experienced was many years ago. A service I worked on received unexpected metadata from one of its dependencies. That metadata caused the service to fail, but it's also got cached. After a little while, we realized that in order to recover our service, we needed to clear the metadata, we needed to clear the cache metadata and restart the service. What we didn't account for was at the time was that when our large fleet restarted with cold caches, it needed to rehydrate itself. And as you can imagine, that wasn't an action we performed very often, and certainly not across the entire fleet at the same time. So this unexpected load brought the whole system down to its knees. And eventually, we managed to bring the system back to life, but a recovery that could have lasted a few minutes lasted a few hours. We learned that day that we didn't have a system that was easy to recover on our hands. If you're wondering if your service has similar risks, there might be warning signs that you could look for. Take a look at your deployments or your fleet operations. If your deployments are unintentionally slow, or if your containers or your hosts take sometimes occasionally fail to start up with transit errors. Or if you have complex runbooks to scale up or down your service, these may be small quality of life problems during normal times, but they're also telltale signs that your service might be hard to recover when you need that most. And so, needless to say, one of the lessons our team took away from that event is that we needed our service to cold start much quicker and much more reliably. And to do that, we needed to actually start paying attention and focusing on that behavior, on that code path, and start thinking differently about our dependencies. But it doesn't just end there. One of the things we've also noticed is that when large scale systems fail, its clients don't just patiently wait. They tend to pile on, retrying their requests while waiting for recovery. And it's actually not unusual for the load on the service to actually go up during an outage. And when your service starts up, its caches and connection pools tend to be cold. And if you're not careful, this combination of cold code path and additional load can bring this service down again, just bring this newly recovered service down again. And so what we really want is for our service to do some light jogging before it jumps into the race. And again, there are number of approaches that can work. For example, a lot of services are fronted by a load balancer or by a reverse proxy. And if your support slow start functionality, you can enable that. What slow start does is instruct your load balancer to ramp up the traffic to fresh targets slowly. At Amazon, we also insist that our services have throttling controls, and those two can be a great tool, here. And now your service may need a different mechanism, but what you really want is to have a way to control the speed at which you open up the fire hose. You want your service to warm up slowly without destabilizing. And after we've invested in making our services easy and quickly restartable, we saw another benefit too. Such services could scale up really quickly as well. And it turns out that can also be a useful tool during outages. A common symptom of failures in complex systems tends to be resource exhaustion. And that can happen even when your service is appropriately scaled for the load it expects to handle. And if you run into this situation, sometimes the fastest and the simplest thing to do just maybe to throw a lot of additional capacity at a struggling service. As an example, our teams can often begin proactively scaling out the service, even at the smallest suspicion that such resource exhaustion might be in play, even when they might be still pursuing other recovery options at the same time. And obviously, your finance team may not be happy if you stay in that state for too long, but remember, we are prioritizing recovery. Later on, when the dust settles and we fix the actual problem, we can actually scale the system back down to reasonable levels again. The last recovery pattern I want to talk about today is the role of change in complex failures. When we look across the industry and our own systems, we see that change often is one of the leading causes of failures. And it can really be any change, no matter how trivial or how well tested. And when dealing with such failures, we want our teams and our tooling to bias towards proactive recovery, proactively rolling back any change that has even the remote chance of being the trigger. And in fact, we don't even want to wait for a confirmation. The challenge, however, we often see is that complex systems are in a constant state of change. New software versions are being deployed, new feature flags are being enabled, dependencies might be changing their behavior, hosts are failing and being replaced by new ones. And at the same time, operators might be changing system parameters while platform teams are changing the infrastructure underneath the service. And so it can be challenging to even find out what changes were made to the system or its dependencies. Perhaps if your organization is small and everybody is within the shouting distance, you can just stand up and ask. But for complex systems with many distinct components, that just tends to be impractical. To help that, one of the simplest approaches we can take is insist that every change to the system, no matter how small or trivial, is safely and easily reversible. And then it also must produce a durable audit log. Then, in an unlikely event of an outage, our automation or our operators can quickly examine that audit log for recent changes. And if there are changes where the timelines correlate, we can just speculatively undo them, hoping for that leads to a quick recovery. And then when the pressure of the outage is over and the failure is well understood, the team can decide which changes are safe to roll forward again and which one was an actual culprit and requires a fix. I want to wrap up with a few key takeaways. Complex systems rarely fail due to simple causes, precisely because they've already been engineered to be resilient to those. Instead, complex systems tend to fail due to interplay of multiple unforeseen factors. How complex systems fail is a great essay by Dr. Richard Cook, one of my favorites, that examines this dynamic in depth. And so, when dealing with such failures, we want our services and our teams to optimize for how to recover the system quickly, even if that means not understanding the root cause at the time. And to do that reliably, we've learned that there are a number of implementation choices we can insist on making that help make our systems easier to recover. And we still never want to have an outage. But if we do that right, recovering from an unexpected failure can take minutes instead of hours. And in the real world, that can make a huge difference. Thank you, and I'm looking forward to your questions.